Now we'll study directional derivatives and the gradient vector. So far, you learned how to get partial derivatives. If z is f of xy, then the partial derivatives f sub x and f sub y represent the rates of change of z in the x and y coordinate directions. Rather than for only coordinate directions, we'll try to get derivative in arbitrary directions. How? We'll use techniques used for partial derivatives. Let's go back to section 14.3, partial derivatives. When we try to get f sub x, for example, we first considered a vertical plane passing the point parallel to x-axis. Then the plane intersects the surface, making this curve. And along the curve, we try to find the slope of the tangent line. That is the partial derivative in x direction, f sub x. For f sub y, and similarly we consider vertical plane parallel to the y-axis and passing the point. Then we have intersection, this curve, and we can get the slope of the tangent line. Then that is f sub y. We did exactly the same way. We'll try to get directional derivative. Now, this is point, and this is direction we decided, a unit vector in u direction. Now consider a plane passing this point and parallel to the direction u, so including the vector u. Then that's the plane, and we have intersection here, the curve, and along the curve at the point, we'll try to get the slope of the tangent line. That's the directional derivative of f in the direction of u. That's the geometric interpretation. Algebraically, we can define the directional derivative in this way. duf is indicating u direction as limit as h approaches 0, the average slope. This point is a perturbation of that one. You can easily see from here, this point is same as the base point plus h times the vector AB, and that is exactly the same as this one. So the base point plus h times u. U is a unit vector, so that this point is perturbed from this one in u direction, having distance h. So we divide by h. So that one is the average slope in u direction. As h approaches 0, once the limit exists, then that's the directional derivative. Okay, so that's the definition. Now, for this definition, maybe if we try to use the definition to get the directional derivative, then it may be complicated. So we need a little bit convenient computational formula. In order to get a convenient formula, we need a little bit of mathematics. This numerator can be written into these two parts by subtracting this quantity and adding the same. Now divide by h. So divide by h for that one. Divide by h, we have that. Rather than h itself, we put a here, a, and b here, b. Okay, that'll be quite clear with this explanation. Now, these two are in y direction the same. They are not the same as y0. However, as h approaches 0, these two will approach y0. Now, the perturbation is this one. From x0 in x direction, HA perturbation, so that we put HA. So it is a kind of a average slope in x direction. Once it has a limit as h approaches 0, then that will be x directional slope f sub x. Now look at this one, x0 the same. This one is perturbation in y direction, HB. So divided by HB, and once limit exists as h approaches 0, then that must be y directional derivative. So here, these two terms will converge to a f sub x plus b sub y. Here a and b. Okay, so we have here a theorem that's for computation. If f is a differential function of x and y, then f has a directional derivative in the direction of any unit vector u, ab, and the directional derivative duf is now f sub x times a plus f sub y times b. We got this one from the derivation. Now, it can be written as in this dot product form. So we have here f sub x, f sub y, the vector, dot the directional unit vector. This is true for arbitrary choice of the vector u. So for every direction, we can get directional derivative. So eventually the directional derivative is the slope along the direction. Okay. Find the directional derivative duf if f is given in this way and u is the unit vector given by the angle theta pi over 4. Then clearly the unit vector can be written in this way: cosine pi over 4 and sine pi over 4. That is this one. So we got u, and to get the directional derivative, we need f sub x and f sub y. And we have to evaluate the partial derivatives at 2 and 3 to get the value. Okay. Now f sub x, x derivative, and this is 3x squared, and that is plus 2y. Okay, that is 2y, and y to the 4 will disappear. F sub y, y derivative, then that is 2x, this will be 0, and that is 2x, and plus 4y cubed. And when we are using the point 2 and 3, x is 2, y equal 3, then x equal 2, then that will be 12. Okay, 12 plus 6, so that is 18. Now that is 2x, that is 4 plus 27 times 4, which will be 108. So that is 112. Okay. So we have here DUF at 2, 3. That is same as f sub x at the point, and a is 1 over square root of 2 plus f sub y, and 2 and 3, and 1 over square root of 2. Okay, that's this one is 18 and times 1 over square root of 2 plus f sub y 112 times 1 over square root of 2. So we have here 130 times 1 over square root of 2, which is same as square root of 2 over 2. So that 65 square root of 2. Okay, that's the final answer. Okay, so that is the corresponding picture. There's DUF in the direction. Okay, we have a note. The only reason we are restricting the directional derivative to the unit vector is because we care about the rate of change in f per unit distance. So it must be an average slope, so that as h approaches 0, it must be instantaneous slope. Okay. If the unit vector u makes an angle theta with the positive x-axis, then u must be cosine theta, sine theta, and at the moment, the DUF must be given in this way. Okay, this is a summary from the earlier problem. Find the directional derivative of f of xy, given in this way, at the point 1, 0 in the direction given by the angle theta pi over 4. Then u is now cosine pi over 3 and sine pi over 3. Okay, what is the cosine pi over 3? That is 1/2, and sine pi over 3 is square root of 3 over 2. Right? Okay, we got the direction, and we have to get f sub x and f sub y. F sub x as x derivative, then there's 1 plus, for the block, we make derivative, then there's cosine xy, and the derivative with respect to x will make y. Okay, now f sub y, that will be 0, and this cosine xy, y derivative will make here x. Now we use the point, which is now 1 and 0. Then x is 1, y equals 0. Okay, this will be 0, so that is 1. X is 0, x is 1, y equals 0. Cosine 0 is 1, x is 1, so that is 1. So f sub x, f sub y is 1. So du of f, that is, now we are using dot product, the formula, 1 and 1, there's f sub x and f sub y, dot. And here, 1 over 2, and square root of 3 over 2. So that's simply multiplication, and add. So that is same as 1 plus square root of 2 over, okay, that is 3 over 2. Right? That's the final answer. F is given here. Now, rather than two variables, we may consider directional derivatives for functions of 3 variables. Now, the function is defined in this way. X, Y, Z are independent variable, and we'll try to find the directional derivative of f at 1, 3, 1. The point is given in the direction of v. Okay, that's the direction, but when you try to get directional derivative, you need a unit vector. So u can be found, we have to have the same direction. So from v divided by its length, we can get u. Now, what is the length? Is length of v is same as square root of squared, second component squared, and third component squared, so that there is a square root of 9, which is 3. Okay, that is 3. So the unit vector in the direction of v is 1/3 times 2 minus 2 minus 1. Okay, that's the unit vector in the direction. Now we have to get f sub x, f sub y, f sub z. F sub x, that is 2x. F sub y, that is minus 4y, y derivative, and f sub z, z derivative, that is 4z cubed. Now the point is 1, 3, 1, x is 1, y equal 3, z is 1. So that now we are using here 1, 3, 1 at the point. We have to evaluate. Then x is 1, then is 2. And y is 3, minus 12. And z is 1, that is 4. Okay? So duf, okay, that must be this portion will make 2 minus 12 and 4 a vector. And now u vector, directional vector is 1/3, and 2 minus 2 and minus 1. Okay, there's 1/3. The constant will go out, and this one is 4, the multiplication, and now there is 24, and there is a minus 4. Right? So you can simplify to get the final answer. Okay. Now we define f sub x, f sub y. This one, this pair appeared a lot in practical computation. Like over there, in these examples, we try to get an f sub x, f sub y, and for functions of 3 variables, we'll try to get f sub x, f sub y, f sub z. So we may give a name for this group. Okay, that is the gradient. F is the differentiable function of 2 variables, x and y. Then the gradient of f is the vector function, and we are using notation. Del f is not really del. This is nabla. Nabla f equals f sub x, f sub y, the vector. And we may write in this way, and x partial derivative I plus y partial derivative j. You can write either way, but this one has a name, so we call it the gradient for function of 2 variables. Once it has a 3 variable, then gradient of f at x, y, z, then now there's f sub x and f sub y and f sub z, or 3-dimensional vector. So just we can expand the definition for functions of 2 variables to functions of 3 variables quite easily. That is gradient vector. Okay. Now f of x, y is given, and find gradient of f and gradient of f at 0, 1. Okay, let's do that. Here, gradient of f. Now, it has two components, x derivative and y derivative. For this one, x derivative is cosine x, and plus, for this one, y e to the xy. Okay. Now, y derivative, that will be 0, and y derivative of this one will make x e to the xy. So that's the gradient. You can write as a vector and side by side or vertically. It doesn't matter. That is gradient vector. Now, we try to get the numeric value when x is 0, y equal 1. Then x is 0, that's 1. X equals 0, and y equal 1. 1 and 0, so that's 1 plus 1. Now, x is 0, so no matter what it is, the value must be 0. So that we have here 2 and 0. Okay? With this notation of the gradient vector, we can write the directional derivative duf in this way: gradient of f dot u. And if u is ab, the two components, then f sub x a plus f sub y b. Now, look at that one. And directional derivative is the same as, we can say in this way, dot product is projection to the vector. So we can say this one in this way. The gradient vector is projected in u direction, to the u direction, then that is the directional derivative. And that one is quite useful later on when we try to maximize the directional derivative. But anyway, here duf is gradient of f and u dot product. Okay, so later on we'll consider some details about maximizing directional derivative. Find the directional derivative of f of xy equals this one at the point 2 and minus 1 in the direction of the vector. Okay, now the direction is given, and so we have to find the unit vector in the direction. So u must be v over the length of v. And from this one, length of v, that is square root of 30 squared, 9, plus 4 squared, 16, so that is a 5. Okay, so that is same as 1 over 5 and 3 and 4. That is the unit vector in the direction of v. So we found the u. Now we have to get gradient of f. Gradient of f. Now x directional derivative is 2x y cubed, and that will be 0. And y directional derivative 3x squared y squared and minus 4. So that's the gradient vector. And at the point 2 and minus 1, x is 2 and y is minus 1, we can get the numeric value. X is 2, y is minus 1. So it's minus 1, 2, so that minus 4. And x is 2 minus 1. That is 3 times 4 times 1, 12 minus 4, which is 8. Right? So the directional derivative df is same as gradient of f dot u. Okay. So the vector is -4, gradient vector is -4 and 8. Just a moment, there's 8. And now u vector is 1 over 5 and 3 and 4. So we have 1 over 5, the constant, and this multiplication is -12. That one is 32. This is 20 divided by 4. So that is divided by 5. So the final answer must be 4. Okay. We'll continue in the second part. Thank you.